So this is, we may have a propositional function px, and then we may have a proposition there exists xpx. So if we want to show that there exists xpx to be true, then the simplest way is we find the x for you. Okay, so there exists a number such that the square is equal to itself. Okay, so you can find a number for me. If it works, then it is already done. So 0 is such a number. So 0 is a number such that the square is itself. Okay, 0 squared is equal to 0. Or you can say 1. 1 is another possible x that proves that this is correct. So if this is the case, we can find a certain x. So we can find a certain x0, a specific x0 that makes it to be true. Then we can show that this is correct. And such an x0 is called a witness. Okay? Okay? It's called a witness. And sometimes we may, so to prove that this is true, is equivalent to showing that for every x, px, sorry, it is the same as we are showing this is false. To show that there exists some x which makes px to be true, it is equivalent to show that if we are claiming for every x not px, then there is something that will make this part false. Is that okay? Yeah, this is the De Morgan's law. If a certain x0 that makes a statement, if a certain x0 that makes this one false, then we give it another name. We don't call it a witness. Witness is something that proves something to be true. Okay. When we prove something to be false, then the witness for proving something to be false, we will call it a counter example. This is an example that's counter your argument, that is against your argument. We find an example which shows that your statement is false. Then in that case, this is a counter example. So for instance, again, so we can change the previous argument. It's like for any number, you cannot find a number such that the square is equal to itself. Now this one is wrong. Okay, this one is wrong. How we can show that I'm wrong? You find me a counter example. You find me a certain x, which means that the square of this one is really equal to itself. So you can use 0 or 1 as an counter example in this case. Is that okay? Okay, so these are some concepts. Okay, so usually finding existence proof, you either find it by luck, yes, or yeah, mostly by luck. Okay, so let's take a look of this number 1729. So what's so special about this number? This number has a name. Okay, this number strangely has a name. This one is called Ramanujan Hardy number. Wow, how come a number has a name? Okay, so this is called Ramanujan Hardy number, or Hardy Ramanujan number, wherever. Okay, so these two are mathematicians. So Hardy is a very well-known number theorist. So he works in number theory. Okay, I think he is a professor in I forget, Oxford or Cambridge, Cambridge maybe. Okay, and Ramanujan. Let's guess, what is his nationality? Which country does he come from? Looks like what kind of a name? Indian, very good. So Ramanujan is an Indian, okay. So he's a genius, okay. Yes, really, he is a genius. He studied math by himself. Oh, it's like a Chinese, so there is also a Chinese genius who studied math by himself and becomes very famous. So there is a Chinese mathematician who has only maybe primary school graduate, but he studied mathematics of himself and later becomes a professor in Tsinghua University, not ours, but in Beijing. Anyone know who he is? Okay, Hua Luo Geng. Okay, so this is a Chinese one. Okay, so he becomes a professor in National Tsinghua. No, not I don't know what his name. Okay, Tsinghua University, and then he died when he was having a conference in Japan. Okay, so he's dying overseas. And this Ramanujan is also a genius. He also studied mathematics by himself. Okay, so one day he sent a letter to this Hardy, and then Hardy read Ramanujan's letter. The letter is full of a lot of formulas. So a lot of very, very strange formulas. So these formulas are something like summation of blah, 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 is equal to blah, 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 blah. Okay, a lot of them, maybe 100 of them. And then Hardy says, okay, wow, this one is either two possibilities. So one is he must be either a genius or he is a Freud, someone who is pretending he is to be very smart. Maybe he's just copying a lot of these kind of strange equations, very beautiful, strange formulas into this mail. But so Hardy consulted. Okay, go and ask his friend. So Hardy has a friend. His name is called Littlewood. Okay, Hardy Littlewood. Okay, so this Littlewood says that okay, let's go and check whether this one is to be really a genius or a Freud, because out of those formula, a lot of them Hardy has seen that before, but there are still many of them. So 100, let's say there are 100 equations, 100 formulas. A lot of them are very, very beautiful formulas Hardy has seen already, but some of them Hardy has never seen. Okay, and there is no proof. Okay, just write down the formulas. Okay, so they decided to invite this Ramanujan to visit them from India to England. And it turns out that this Ramanujan is a genius. Okay, he has over his life a lot of formulas, okay, produced, and then they are amazing. Okay, now, so why there is a number called 1729? Okay, so one day this Ramanujan gets sick and then was in the hospital. And then Hardy is a very, very shy person. Okay, Hardy is so shy that there's actually nearly never any photo of him. Okay, he's afraid of taking any photos. Okay, maybe this photo will absorb his soul inside. Okay, so, and then he doesn't know how to communicate well with the others. Okay, very, very shy. So every time, okay, so Ramanujan is sick and then in the hospital, and then he tried very, very hard to come up with something to talk with Ramanujan. He couldn't find it. Okay, so he go to visit Ramanujan and says, okay, so today I took a taxi to come to visit you, and the license plate was so boring. So the license plate is 1729. It's so boring. I can't find any interesting thing about this number. And then Ramanujan says immediately, so this is very, very strong. Immediately he says that, oh, no. 1729 is very special. It is the first number that can be written as the sum of two cubes. So it can be written as a certain cube plus another cube. Okay, so it's like 1 cube plus 12 cube in two different ways. So it is also 9 cube plus 10 cube. Okay, so this is the first positive integer that you can write it down in the sum of cubes in two different ways. So that's why we now have this number called Ramanujan-Hardy number. Okay, so why is it existence proof? Okay, so it is a number that proves that there is a certain number that you can write it down as the sum of two squares. Is that okay? Okay. This is a witness of the following proposition. There exists a number which can be written as a sum of two different squares. Okay. Of course, a positive number. Okay. Okay, so this is a story about Ramanujan and Hardy. Okay, but existence proof sometimes. Oh, so let me talk a little bit more about Hardy. Okay, about Ramanujan maybe. So take a look at this one. So you have a square. square 1, you know. What is square root of 1? Square root of 1 is 1, okay? Is that okay? You can now look at square root of 1 plus square root of 1. So what is it? So it is equal to square root of 2, right? Of course, you can use your calculator to find out what is square root of 2. You can further talk about square root of 1 plus square root of 1 plus square root of 1. Is it okay? So this is going to be square root of 1 plus square root 2. Is it okay? Is that okay? And you can define the number like this. And then we want to ask, what is this value? What is the value of this one? Okay. So first of all, is it well defined? Okay. Is it well defined? So somehow it seems that it is well defined. Okay, the reason is that later we can show that this number can never exceed 2. You can show that this number can never exceed 2. Okay. So later we will talk about a technique called induction, and you can show that this number is never exceeding 2. It is less than or equal to 2. Okay. But then this number, if you have more terms added, it will increase. Okay. So you start with square root of 1, right? And then you become square root of 2. Okay, square root of 2 is bigger than square root of 1. And then next we'll have square root of 1 plus square root of 2. So square root of 2 is something like 1.4. So it is square root of 2.4. So it is larger than square root of 2 already. So this one, if you add more terms here, it will become larger and larger and larger. Now it becomes larger and larger and larger, but it can never be greater than 2. What does it mean? Limit. So the limit will exist. Okay. Yeah, limit means that it will never grow forever, because if it grows forever, it will eventually exceed 2. So if it cannot exceed 2, there must be some place that it stops growing, okay, in the end. So the limit of this exists. So if the limit of this exists, we can talk about what is the limit of this, okay. Okay, so for this one, there is an interesting way to show. So you can say this is equal to x. Is that okay? Okay, x is equal to this one. So x is equal to what? X is equal to the square root of 1 plus x. Is that okay? Is that okay? And then so you solve this, you will get x squared is equal to 1 plus x. And then after doing this quadratic equation, you solve it. Then you'll find there are two possible roots for x. One of them is positive, one of them is negative. So one of them is equal to 1 plus square root 5 over 2. This is equal to 1.618, blah, 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 blah. And this is the golden ratio. Okay, so it will grow and then grows up to this golden ratio. Okay, now for this one, you can solve it. And then Ramanujan created a different sum. Okay, this is what he has created. This is square root of 1 plus 2 times square root of 1 plus 3 times the square root of 1 plus 4 times the square root of 1 plus dot dot dot. This is what he is proposing. Okay, so he asked this question in a mathematical journal, and sadly nobody could answer this. So he gave the answer afterwards. Okay, so I'll give it to you, and then if you have time, we will talk about this. Okay, so yeah, this is a puzzle. You can think of this as a puzzle, and then someone created it. Somehow we cannot use the same technique to prove. The reason is that this part does not look like the original part. So you cannot use a certain x to represent it. But instead of using an x, you use a function to represent it. So there is a function to represent this. Okay? Now talking about existence proof, there is one of them which is also very, very amazing. Okay? So we have learned about irrational numbers, right? So irrational numbers. So irrational numbers looks like it is nothing to do with integers because it is not a ratio between two integers, right? And it is nothing to do with rational numbers because rational are integers. Okay, but this question is, this is the question. Prove that we can find there exist irrational numbers. There exist irrational numbers A and B. So we can find two irrational numbers such that, okay, such that what? Such that A to the power B, wow, this is strange, right? Is rational. Wow, this looks pretty amazing. Okay, so an irrational number's irrational power becomes rational. Okay, how can we show? Okay, this is a good, very, very interesting example. So, what is something that is close? Okay, so can you find an irrational number such that, so if B becomes, okay, if we just need A to be irrational, is there any irrational number such that the power of it becomes rational? Yes? Which irrational number we know? We know square root 2, am I correct? Square root 2. So how to make square root 2 rational? By raising it to 2, very good. If you raise it to a power of 2, then it becomes 2. So it becomes rational. Is that okay? Now, this is A, but this cannot be B, okay? Okay, so what can we do? Let's do something strange, okay? Let's look at this square root 2 to the power square root 2 times square root 2. So what is it? So square root 2 to the power square root 2 times square root 2 is equal to square root 2 of 2, right? So this is equal to 2. So this is rational, right? And then this is equal to what? This is equal to square root 2 to the power square root 2, this number, to the power square root 2. Is it? Let's take a look. Okay, 2 to the power 3 times 4. And 2 to the power 3 to the power 4. So what is 2 to the power 3 to the power 4? 2 to the power 3 to the power is 2 to the power 3, 2 to the power 3, 2 to the power 3, 2 to the power 3. Is it okay? So it is 2 to the power 3 times 4. Is it okay? So here is square root 2 to the power square root 2. Okay. Is it rational? No, we don't know actually. Okay, I don't know. It looks like irrational. I think this is irrational, but there are two cases, proof by cases. Either this one is irrational. Now, if this one is irrational, then what do we have? Then we have irrational to the irrational becomes rational. Okay? Okay, so case one is this part is already irrational. So we have this part as A and this part as B. This is case one. But this may not be the only case, right? What is the other case? The other case is this part is rational. Am I correct? If this part is rational, then you use this as the A and you use this as the B. Then you have this part to the power of this part is rational. Do you understand my point? So there are only two cases. In this world, there are only two cases. Look at this number, square root 2 to the power square root 2. There are two cases. Either this is irrational, or the other case is this is rational. Is that okay? Now, if this is irrational, I will set A to be square root 2 to the power square root 2. I will set B to the equal to square root 2. Then you will have this one to this power. This is irrational. To the power irrational becomes rational. Is that okay? On the other hand, if you now know that square root 2 to the power square root 2 is rational, if you know that this is rational, then I cannot use this as A. Because this is rational, I cannot use it as A. A needs to be irrational. But yet, I can set A simply to be square root 2, and then B is equal to square root 2. Then square root 2 to the power of square root 2 is equal to square root 2 to the power of square root 2, and it is rational in our case. Is that okay? So no matter we are in this case or in this case, we can find AB. All cases we can find AB. Then done. Okay? Okay? So here, this is a very interesting proof. This is an existence proof. We show that certain things exist. But then we are not really finding exactly what is the correct one. We don't know. But we know that it is still existing. Okay? So either this case or this case will be the correct answer for the A and B that we want to choose. Okay? So this is one of the very amazing proofs that I've seen. Okay? So, yeah. And simple, right? Simple enough. Okay, now we have some time. Let us take a look of some. So we have seen a lot of proofs. Let us take a look of some common mistakes in the proofs. So these are going to be very important, okay, in your exam or in your further studies. Okay, you need to know whether you are making a mistake or not. Now here we are going to show. So I'm going to give you a very wrong proof. We are going to show that 1 is equal to 2. Okay. Okay, 1 is equal to 2. So the first one is, let's assume that A is equal to B. Let's say this is a premise. So this is a given thing. We start with given thing. So using A is equal to B, then we can say, let's multiply both sides by A. So we have A squared is equal to AB. Okay? So you have the reason. Multiply A onto both sides. Then we will have, let's deduct B squared from both sides. So A squared minus B squared is equal to AB minus B squared. Is that okay? Now because of this, then we can do factorization. A squared minus B squared turns out to be equal to A plus B times A minus B. Is that okay? And then AB, it is B times A minus B. Is that okay? Now if 4 is correct, then we have 5. So we cancel the factor A minus B from both sides. So we will have A plus B is equal to B. And then at the 6th step, A plus B is equal to B. We use the given condition A is equal to B. So it is 2B. So B plus B is equal to B. Is that okay? And then the last one is we will have 2 is equal to 1. What's wrong? Yeah, there must be something wrong, right? Where? Two places. There are 2 places. One is more critical than the other. So which part is wrong? Is it wrong to multiply A on both sides? No, nothing wrong here. Is it wrong to minus B squared from both sides? Is it wrong to factorize them? Is it wrong to make this into A plus B equals to B? Yes. Yes, okay, so this is, why? Because, very good. We cannot be sure that A minus B is not 0. Okay, if it is not 0, then we cannot cancel both sides. Okay, now we can still continue. Assume that this is still correct. We may still assume that this is still correct. Is it wrong to make this into 2B equals to B? So assume that you know A plus B is equal to B. Is it wrong to make it into 2B equal to B? So assume. Okay, let's assume that for some reason, A plus B is really equal to B. Is it wrong to assume that to make 2B is equal to B? No? No, nothing wrong. Okay, I should say. Because really, if this is correct, then this has to be correct. How about this one? If 2B is equal to B, is it true to say that 2 is equal to 1? No. Okay, again, this is not correct because we are dividing B from both sides. You are not sure whether B is equal to 0 or not. So there are 2 places that are wrong. And this is more wrong than this one. Okay, wronger. Okay. Okay, so this is the first one. Okay.